Hey, geometry genius. We're here, back, talking about Pythagorean theorem in a way, but really specifically special right triangles. What are these? What do they do? They're really helpful, so we're going to take a look at them. We're going to be given one side length of a 45, 45, 90 right triangle. We'll be asked to find the other two. We'll also see the 30, 60, 90 right triangle, finding the other two sides using special right triangles with select properties to solve application problems. So previously we were talking about the diamond setup for a baseball diamond, which we said was a square that had the diagonal cut through, and we found the measurement from home plate to second base directly. But when this diagonal was cut through, what was this angle? And this angle? What were those two angles going to have to be if this was bisected because of the diagonal? Should be saying 45 degrees. So what's cool is that that's a special type of right triangle that has a very specific pattern that we'll learn about now. So the acute angles of a right isosceles triangle are both 45 degrees. Another name for these right isosceles triangles is 45, 45, 90. If each leg has a length of x and the hypotenuse has a length of y, you can solve for y in terms of x using the following Pythagorean theorem setup, which we actually did, which is going to say that eventually the hypotenuse is equal to the side leg multiplied with the square root of 2. So take a moment, pause, take this information in, and we'll chat about it. And definitely copy this information down because this gets used a ton. So I know that if this is a triangle, obviously a triangle because it mentions it here, I know this is an isosceles triangle because these two sides are claiming to be congruent. So I'm allowed to also say that this is 6 units. And then since this is an isosceles right triangle, I know that this angle is congruent to this angle. So these two angles in particular are going to be 45 degrees. If you're not convinced, sketch it out, but that makes sense. So what's cool is that when you spot these, you can quickly just say that the hypotenuse, in this case x, is going to be equal to the side leg multiplied with square root of 2. So this would be 6 root 2. And y was 6. And then you're done. Notice, we don't even have to use Pythagorean theorem. We're really just looking at the triangle and saying, oh, it's an isosceles right triangle. It has to be 45, 45, 90. It's going to be pretty simple. Nothing crazy there. We can take this further and solve for the side legs if we're only given the hypotenuse. So in this case, I know that 10 is our hypotenuse. Which we also can say 10 should be equal to our side length multiplied with the square root of 2. Pretty easy. So if we wanted to take this further and try to get a hold of the legs, we know that these two legs are congruent. If we solve this for s, we could divide both sides by the square root of 2. Square root of 2's cancel. In algebra, we really don't like keeping a radical in the denominator because if we're going to divide by an insane decimal, that's not a good look. So in this case, I'm going to rationalize this, multiplying the top and the bottom by square root of 2. Square root of 2's can cancel. Or no, I actually want that to happen. Okay, sorry, don't cancel them. All right, so this would be 10 square root of 2 over just 2 now, because this was square root of 2 times 2. And then can you simplify this fraction? Definitely can. 10 over 2 is going to be 5. Square root of 2 is along for the ride. That's our new side. So this would be equal to 5 square root of 2. This is equal to 5 square root of 2. Pretty simple. Take a moment, try example 4, which you can do as the same kind of setup. 5 square root of 6 should be equal to our side multiplying with square root of 2, make this more like an S. If we divide both sides by square root of 2, you get this 5 square root of 6 over square root of 2 should be equal to S. I don't really like how this is written, so I'm going to see if I can cancel out the square root of 2. And that would leave me with 5 square root of 3 for our side length. If you're not convinced this can be done, square root of 6 can be rewritten as square root of 2 times square root of 3 over square root of 2. Square root of 2 cancels, so 5 root 3 is left over. Easy. We see another example of a special right triangle dealing now with 30, 60, 90. If you want to pause and take a look at this area, you can. But the main idea is that with this 30, 60, 90, we can take a look at our hypotenuse, which is two versions of the smallest side, and the larger side, so the larger leg, is the smallest side multiplied with the square root of 3. So let me draw this out a little bit more clearly for you. So if we have an angle, one that's 30 degrees, one that's 60 degrees, our hypotenuse is two forms of the smallest side. The angle of 30 degrees, opposites that, it's going to be the smallest side. And then opposite of 60 degrees, it's our side times square root of 3. So notice that the side, the smallest side, gets used quite a bit. So the sooner you notice it's a 30, 60, 90, the better off you'll be. You can take a look at this. Our hypotenuse is 10, and I know that the 30 degree one is just going to be the smallest side. I know that the hypotenuse here is equal to two versions of that. So I can say that S equals 5. So this is now 5. And I can take this information further because the side opposite 60 degrees is going to be the smallest side times root 3. So in this case, x equals 5, y equals 5 square root of 3. Simple. Hope this was helpful. We'll see more examples of this in class. If you have a question, bring it. Thanks for watching.